Welcome back to the second episode of our journey through the Calculus Chronicle. In our previous episode, we traced the lineage of this mathematical revolution from the simple calculi, the pebbles used for counting, to the explosive intellectual battle between Sir Isaac Newton and Gottfried Wilhelm Leibniz. We saw how they independently discovered the fundamental link between changing quantities and the areas they sweep out. However, they lacked a solid floor to stand on. Their infinitesimals were criticized as the ghosts of departed quantities. In this episode, we step through the true gateway of modern analysis, the limit. This is the rigorous framework that finally silenced the skeptics and turned intuition into ironclad logic. Before we dive into the infinite, please note that this series is a product of personal research. While I strive for mathematical precision as we explore these concepts, always treat this as a narrative guide to complement your formal studies. Let's solve the paradoxes that haunted mathematicians for millennia. To understand why we need limits, we must travel back much further than the 17th century, all the way to ancient Greece, around 450 BC. Here, Zeno of Elea posed a series of logical puzzles known as Zeno's paradoxes. These weren't just brain teasers. They were existential threats to our understanding of motion and space. Zeno argued that motion is actually an illusion because of the infinite divisibility of space. If you want to move from point A to point B, you must first travel half the distance. But before you reach the halfway mark, you must travel half of that half, and so on ad infinitum. He claimed that because you must complete an infinite number of tasks in a finite amount of time, you can never truly start, nor can you ever arrive. This sparked a crisis. How do we mathematically describe a process that involves infinite steps yet reaches a definite conclusion? Let's look at Zeno's most famous example, Achilles and the tortoise. Achilles is 10 times faster than the tortoise, so he gives the creature a 100-meter head start. Logic tells us Achilles will blow past the tortoise in seconds. But Zeno's math says otherwise. By the time Achilles reaches the 100-meter mark, the tortoise has moved 10 meters further. By the time Achilles covers those 10 meters, the tortoise has moved 1 meter. As Achilles covers that 1 meter, the tortoise is another 0.1 meters ahead. No matter how close Achilles gets, Zeno argues there is always a tiny, remaining gap. This created a profound horror of the infinite in Greek mathematics. They couldn't explain how the sum of an infinite series of smaller and smaller intervals could equal a finite number. They lacked the gateway, the concept of a limit, to bridge the gap between the discrete and the continuous. This paradox highlights why we need a formal way to talk about the infinitesimal, a quantity so small it's almost zero, but not quite. For centuries, mathematicians used fluxions or differentials to describe changes over these tiny intervals, but their definitions were hand-wavy at best. Critics like Bishop Berkeley mocked them, asking how something could be nothing, yet still have a ratio. To save calculus, we needed to move away from the idea of reaching the end of an infinite process and instead focus on what happens as we get arbitrarily close to it. This shift in perspective is the birth of the limit. It allows us to define the exact value that a function or a sequence approaches, even if it never technically arrives there in a finite number of steps. It is the mathematical tool that finally lets Achilles pass the tortoise. When we talk about limits in calculus, we are really talking about the behavior of a function as we move closer and closer to a particular point. Imagine yourself walking along the curve of a function, almost as if you are hiking on a mathematical landscape. Your horizontal position represents the value of x, and your vertical height represents f of x. As you step toward a specific target value, which we call c, you pay attention to what your height is tending toward. The fascinating part is that the limit does not care what happens exactly at x equals c. The function might be undefined there, or it might suddenly jump to a different value. What matters is the trend. If approaching from the left and the right brings you closer to the same vertical value, which we call L, then the limit exists. In that case, we say the limit of f of x as x approaches c is L. It is less about the destination itself and more about the journey toward it, even if that destination is a missing point or a cliff in the graph. To see this in action, consider the function f x equals x squared minus 1 divided by x minus 1. If you try to plug in x equals 1, you get 0 divided by 0, which is mathematically undefined. The function literally doesn't exist at that point. However, if we look at the values around x equals 1, a pattern emerges. As we plug in 0.999, we get 1.999. As we plug in 1.001, we get 2.001. It is blindingly obvious that the function is heading toward the value 2. In the language of calculus, we say the limit exists and equals 2. This allows us to fill in the holes left by algebra and understand the behavior of functions in regions where they appear to break down. This is the power of the limit. It gives us information about the impossible by examining the nearly possible. Sometimes, a function doesn't agree on where it's going. This brings us to one-sided limits. Imagine a staircase function where for all negative x, the value is 0, but for all positive x, the value is 1. If you approach 0 from the left, the negative side, you'd swear the limit is 0. If you approach from the right, the positive side, you'd swear it's 1. In calculus, we denote these as limit x tends to 0 minus f of x and limit x tends to 0 plus f of x. For a general limit to exist, these two one-sided perspectives must agree. If they don't, the limit simply does not exist at that point. This distinction is vital for identifying jumps and breaks in our mathematical models, ensuring that our gateway only opens when there is a clear, unified destination. For over a century, the closer and closer definition was enough for most. But as mathematics became more complex, closer and closer wasn't precise enough for the skeptics. In the 19th century, mathematicians like Augustin Louis Cauchy and Karl Weierstrass decided to replace intuition with rigor. They introduced the formal epsilon delta definition of a limit. This is often the point where many students feel the gate slamming shut, but the logic is actually quite beautiful. It turns the limit into a challenge-response game. If you claim the limit is L, I can challenge you with a tiny distance epsilon. I ask, can you keep the function within epsilon of L? You respond by finding a distance delta around C. If you can always find a delta for any epsilon I throw at you, the limit is proven. The mathematical notation for a limit, specifically the symbol lim and the arrow used beneath it, evolved over several centuries as calculus moved from intuitive descriptions to a rigorous formal language. Leonhard Euler was the first to use a symbol for limits of integration in the mid-18th century, though he used brackets and the Latin words ab, from, and ad to. The modern abbreviation lim gained prominence in the early 19th century. Augustin Louis Cauchy systematically used the concept in his 1821 work Cours d'analyse, helping to standardize the term, although he still often wrote it out or used slightly different formatting. The most recognizable part of modern limit notation, the arrow indicating the tendency of a variable, is a relatively recent invention. John Gaston Leatham introduced the arrow symbol in 1905 in his tract surface and volume integrals. It was quickly popularized by G. H. Hardy in his influential 1908 textbook, A Course of Pure Mathematics. Before this, mathematicians often used a semicolon or equals sign to separate the variable from its target value. Let's break down that wall of symbols. The phrase, for every epsilon greater than 0, means no matter how small a margin of error you give me vertically. The there exists a delta means I can find a corresponding window horizontally. The implication states that if your x value is within that horizontal window, the delta neighborhood, then your function's value is guaranteed to fall within the vertical margin of error, the epsilon neighborhood. This definition doesn't rely on motion, or time, or getting closer. It is a static, logical statement about the relationship between two sets of numbers. It transformed calculus from a set of clever tricks into a rigorous branch of mathematical analysis. It is the steel in the gateway of the limit. You might wonder why we need such a headache-inducing definition. The reason is that intuition often fails us when we deal with the infinite. There are functions that are so noisy and jagged that they look continuous but aren't, or functions that have limits at some points but are chaotic at others. Without the epsilon delta definition, we couldn't prove the fundamental theorems that make physics and engineering possible. It provides the proof of work for our calculations. By establishing this high bar for truth, Cauchy and his peers ensured that the skyscraper of calculus was built on a foundation of solid rock, rather than the shifting sands of infinitesimal ghosts. It allows us to move forward with absolute certainty. Now that we have the limit, we can define the most important property for any practical function: continuity. Intuitively, we say a function is continuous if you can draw its graph without lifting your pencil from the paper. It implies a sense of unbrokenness. In the real world, we assume most things are continuous: your height over time, the temperature in a room, the position of a car. But in mathematics, continuity is a high standard. A function can fail to be continuous at a single point, or it can be broken everywhere. The limit is the tool we use to diagnose these breaks. Without continuity, many of the powerful shortcuts of calculus, like the rules for derivatives, simply fall apart. To be continuous at a point C, a function must pass a three-part test using limits. First, the function must actually exist at C. There can't be a hole in the domain. Second, the limit as you approach C must exist. The left and right sides have to agree on where they're going. Third, and most importantly, the destination the limit points to must be the same as the actual value of the function. Essentially, the bridge must lead exactly to where the road is. If any of these three conditions fail, the function is discontinuous. This formal definition allows us to categorize exactly how and why a system breaks down, providing a mathematical language for the snap or the jump. Let's look at the breaks in the road. The first is the removable discontinuity. Imagine a smooth road where a single manhole cover is missing. The limit exists. You know exactly where the road is heading from both directions, but at that specific spot, there's just a hole, or perhaps the point has been moved elsewhere. Mathematically, this often happens when a factor in the numerator and denominator of a fraction cancels out. It's called removable because you could fix the function just by redefining that one single point. In calculus, these are the easiest breaks to handle, but they serve as a reminder that the limit and the function value are two very different things. Next, we have the jump discontinuity. This is like a bridge that was built at two different heights. The ends simply don't meet in the middle. As you approach the point from the left, you're at one altitude, but from the right, you're at another. Here, the one-sided limits exist, but they are not equal. This means the overall limit does not exist. We see jump discontinuities in real-world systems like digital signals, where a voltage might instantly flip from off to on, or in tax brackets, where earning $1 extra can suddenly put you into a higher percentage. Understanding these jumps is crucial for modeling systems that have sudden, discrete changes. Then there's the most dramatic break, the infinite discontinuity, often visualized as a vertical asymptote. This happens when the function's value explodes toward infinity as you get closer to a point. Think of 1 divided by x as x approaches 0. The closer you get to 0, the larger the result becomes, defying any finite limit. These represent singularities, places where our standard math breaks down because the quantities involved become literally immeasurable. In physics, these often signal that a model has reached its limit, such as the infinite density at the center of a black hole. Limits allow us to approach these cliffs of the infinite and study the behavior of the universe, right up to the edge of the abyss. Sometimes finding a limit directly is a nightmare. This is where we use the squeeze theorem, or the sandwich theorem. If you have a function f of x that is trapped between two other functions, g of x and h of x, and both of those outer functions are heading toward the same limit L, then the function in the middle has no choice but to head there too. It's a beautiful piece of logic. If you can't calculate the path of the chaotic middle function, just prove it's sandwiched by two well-behaved ones. This technique is a staple for solving complex limits in trigonometry and advanced calculus, showing that even when things get messy, we can use the boundaries of what we know to define what we don't. We've talked about x approaching a specific number, but what if x just keeps growing forever? This is the limit at infinity. We ask, as our input gets larger and larger, does our function settle down? For the function 1 divided by x, As x goes to a billion, a trillion, a quadrillion, the value gets closer and closer to zero. This defines a horizontal asymptote. Limits at infinity are how we predict the end state of systems. Will a population stabilize? Will a radioactive isotope eventually disappear? Will a moving object eventually come to a halt due to friction? By looking toward the infinite horizon, limits allow us to see the ultimate fate of the mathematical models we build. To make limits practical, we rely on a set of limit laws. These are the algebraic tools that let us break down complex problems into smaller, manageable bites. If you know the limit of $f$ and the limit of $g$, you can find the limit of their sum, their product, and even their quotient, provided the bottom isn't zero. These properties are the workhorses of calculus. They allow us to move from the abstract epsilon delta proofs to efficient calculation. Without these laws, every calculus problem would be an exhausting climb. With them, we have a paved road through the gateway. They represent the grammar of the language of change, allowing us to construct complex mathematical sentences with ease. One of the most common sites at the gateway of limits is the indeterminate form, most notably 0 divided by 0. In basic algebra, 0 divided by 0 is a forbidden sin. But in the land of limits, 0 divided by 0 is a question, not an error. It tells us that there is a competition happening. The numerator is trying to pull the fraction toward 0, while the denominator is trying to blow it up toward infinity. The limit is the referee that decides who wins. Through techniques like factoring, rationalizing, or eventually L'Hopital's rule, we can resolve these indeterminacies to find a hidden, finite value. This is where calculus does its best work, extracting meaningful information from the meaningless void of 0 divided by 0. Why do we obsess over continuity? Because it reflects our deep-seated belief in the smoothness of the natural world. If a physical process were truly discontinuous, it would mean things could teleport from one state to another without passing through the states in between. While quantum mechanics suggests the world is grainy at the smallest scales at the human scale, the assumption of continuity is what allows us to use calculus to predict the path of a planet or the stress on a bridge. By defining continuity rigorously through limits, we create a mathematical mirror for the physical reality we observe. It is the bridge between the steps of logic and the flow of existence. One of the most intuitive results of continuity is the intermediate value theorem. It states that if a function is continuous on an interval, it must hit every single value between its starting height and its ending height. If you were 4 feet tall at age 10 and 5 feet tall at age 15, and assuming growth is a continuous function, there was exactly one moment in time when you were precisely 4.673 feet tall. You couldn't skip it. This theorem is a powerful existence proof. It allows us to guarantee that a solution to an equation exists within a certain range, even if we can't find the exact solution easily. It is the guarantee of the continuous gateway. We are now standing at the very edge of the gateway. The limit is the key that unlocks the first major pillar of calculus, the derivative. In our next episode, we will see how the derivative is nothing more than a specific kind of limit, the limit of the slope of a curve as the distance between 2 points shrinks to 0. This is how we solve the problem of instantaneous speed. How fast are you going at a single, frozen moment in time? Algebra can't answer that because speed requires a change in time, and at a frozen moment, that change is 0. But with the limit, we can approach that frozen moment and find the truth hidden within. Long before the formal definition, the limit was used geometrically. Archimedes used what he called the method of exhaustion to calculate the area of a circle. He inscribed polygons inside the circle and circumscribed them outside. As he increased the number of sides from a hexagon to a 96gon, the area of the polygons approached the area of the circle. He was calculating a limit without having the notation for it. This shows that the concept of the limit is an ancient intuition, a fundamental way the human mind tries to grasp the curved and the complex by using the straight and the simple. The limit is the formalization of this exhaustion, turning a geometric trick into a universal logic. Limits don't just apply to functions, they apply to sequences of numbers too. Think of an infinite sequence where each term is half of the previous one. Does the sum of all these terms go to infinity?
No.
As we add more and more terms, the sum limits out at exactly 2. This is the resolution to Zeno's Achilles paradox. We can sum an infinite number of things and get a finite result, provided those things limit towards 0 fast enough. This understanding of convergence is what allows us to work with infinite series, which are essential for everything from computing the value of pi to how your smartphone processes digital audio signals. Now that we've walked through the gateway, we are ready to meet the first of the 2 titans of calculus. In episode 3, we will use the limit to solve the mystery of instantaneous change. We will move from the average to the exact, learning how to calculate the speed of a falling apple at the very microsecond it hits the ground. We will finally see how Newton and Leibniz turned these limits into a calculus, a tool for calculation that changed the world forever. The foundation is set. The logic is rigorous. The next step is the derivative. I'll see you in the next chapter of the Calculus Chronicle.